Okay, so today we're going to cover statistical inference for numeric data. Okay. So far, we've been dealing just with categorical data. Okay, categorical data we had proportions. Okay, and today we're going to introduce statistical inference for numeric data. And there's actually 4 topics that we're going to cover, and today we'll get through 2 of these. Okay, and they're kind of listed out on your formula sheet. And so we have confidence intervals for mu, or for means, based on one sample. Okay, and then we've got confidence interval for mu1 minus mu2 based on 2 samples. And then we will have hypothesis tests for mu based on 1 sample. And then hypothesis tests for mu1 and mu2 based on 2 samples. Okay, and so they're all listed for you on your table of formulas. And today we'll get through the confidence interval ones. Okay, just keep in mind, if you have a categorical variable, that means you are dealing with proportions. And when you're dealing with proportions, you are going to use the z-table. Today we are going to cover numeric variables. Numeric variables, you are doing inference about means, and you will use the t-table, okay, which is the table that we passed out today. All right, so you have a z-table and you have a t-table. T-table is for means, numeric variables. The z-table is for proportions, categorical variables. Okay, and we have a lot of parallels between all of the statistical inference methods that we learned for categorical variables and proportions. A lot of those same concepts transfer over when we are doing statistical inference for numeric variables. So if you understand confidence intervals for categorical variables, there's a chance that you'll understand confidence intervals for numeric variables as well. Okay, and so I'm going to just kind of tick through each of these. Today we'll just set up the formulas, and then we'll do an example, and we'll do that for the confidence intervals for mu, and then the confidence intervals for mu1 and mu2. Okay, let me actually pull up my tables myself. On the table, here's my t-table. On the table of formulas, there is one set of formulas that we did not cover. Okay, and that's up here. Confidence intervals, proportions, 2 samples. You can kind of X that out because we did not cover this, but the other stuff we did. Okay, so we covered confidence intervals for proportions, 1 sample, hypothesis test for proportions, 1 sample, and hypothesis test for proportions, 2 samples. But and then we'll cover all 4 of these, but we didn't cover this one. Okay. All right, let's just go back and we'll just recall and just do a refresh of recall the confidence interval for the proportion P based on 1 sample. Okay, and what did that confidence interval look like? It looked like what? P hat plus or minus what? Z star times the standard error, right? And that's actually, if you look right here, it says p hat plus or minus z star times the standard error. It's right there on your formula sheet also. We got p hat plus or minus z star times the standard error. I want to kind of just label each of these parts here, okay? P hat, this is our best guess for p based on the data. We're trying to make a confidence interval for the value p. P hat serves as our best guess for p. What's the proportion in the population? Proportion in the population is based on the our best guess is the sample proportion. Okay, z star is our critical value, and that comes from the z table, or I just said there's 4 values you need to know: 1.28, 1.645, 1.96, and 2.58. That's the critical value. And SE, this is our standard error. Okay. All right, let's do the confidence interval. So now we'll talk about the confidence interval for mu based on one sample. Okay. All right, so in the middle, we are going to put in our best guess. Best guess for what? Best guess for mu based on our data. Okay, what is the best guess for what mu is based on our data? X bar, right? It's the sample mean. Yeah, mu hat, that's a reasonable conclusion, except if you say mu hat, you're probably talking about the sample mean, and that in that case is X bar, the sample mean. So that's going to go right in the middle. Then we go plus or minus, and then we have a critical value. Now that we're dealing with the t distribution, this is going to be the critical value t star, and we would multiply this, whoops, by SE, the standard error. Okay, so this is still critical value. So the structure of the confidence interval is exactly the same. It's just instead of p hat, we're using X bar. And instead of z, we have a t. And the standard error formula changes. So it's exactly the same, except everything's different. But I'm trying to set it up and to show you that it is quite similar. Okay. All right. When we pick our t star, okay, so t star, choosing t star requires the confidence level and the degrees of freedom. Okay, degrees of freedom, or DF, is going to be n minus 1. N is our sample size, and we just do one less than that. Okay. The concept of degrees of freedom is, you know, we could play some silly game, and I can say, you know, we're going to pick 10 numbers together as a class, and if you guys can pick 9 numbers, and as long as I get to pick the last number, I can guarantee that the average of your 10 numbers will be 100, okay? And it's simple, you know, whatever numbers you guys pick, whether it's like 1,000,000 or 2 or negative 500, all I have to do is I have to just pick the last number so that all 10 numbers add up to 1,000. And if I can make sure that all 10 numbers add up to 1,000, then the average of those 10 numbers will be 100. Okay? And so in that case, when we're picking 10 numbers, 9 of those numbers are free to be whatever they want, but that last number is, you know, kind of restricted. And so the same idea is here with the degrees of freedom. You know, your sample size, you have 1 less degree of freedom. So if you have 10 items, you have 9 degrees of freedom. That's like a very loose idea of degrees of freedom. Okay, this is not mathematically rigorous, but that's kind of the idea behind degrees of freedom. So That's why we call it. All that really matters is that we're doing n minus 1 here, okay? Okay, and that's it. Confidence interval for mu based on one sample. You'd look up your degrees of freedom, you'd go to your t-table, and you'd say, okay, well, if I have 95% confidence, if that's the confidence level I want, and I have a sample size of 10, sample size of 10 means I have 9 degrees of freedom. So 95% confidence, 9 degrees of freedom, my t star is going to be 2.262, right? Do you guys see that on your table? Okay. An interesting thing to note is that when you go to infinity degrees of freedom, the values become the same as your z star values. So 95% confidence at the very bottom is 1.96. For 90% is 1.645. For 80% is 1.282 if you want to carry it out to a third decimal place, and so on and so forth. Okay, but don't worry about that. Okay, so that's what we have here. Degrees of freedom is this, and so let's try an example. All right, so let's say, I don't know, we are interested in the average weekly sales revenue of some vending machine. Okay. So, I don't know. Let's say we pick 12 random weeks. Okay. And, so we look at the weekly revenue for those 12 weeks, and we'll say the average weekly revenue for the selected weeks. I don't know, how much do you think a vending machine sells in a week? Will be the average weekly revenue for the selected weeks is, I don't know, $165.50. Okay, we'll say that. Okay, the average weekly revenue for the selected weeks is this. Okay, and we'll say the standard deviation of those values is, I don't know, $18.22. I'm just making stuff up, obviously. So we'll say let's make a 90% confidence interval. 90% confidence interval for the mean weekly sales in the population. Okay. So the population would be all weeks for this particular vending machine. I'll just do this for you guys. Okay. We got x bar plus or minus t star times the standard error. Our standard error is s divided by the square root of n. Okay, let's go through. We'll label our numbers. 12, what is 12? What letter is this? This is our sample size n, right? Okay, 165.5, what's that? That's x bar, and then standard deviation 18.22, what's that? S, right? This is the standard deviation of those values. So I just plug in. Well, let's look up t star. So t star has how many degrees of freedom? 12 minus 1, I've got 11 degrees of freedom. And we have 90% confidence. So t star is equal to 11 degrees of freedom, 90% confidence, 1.796. So we guys get? T star is equal to 1.796. Okay, so I'm just going to plug in all of these numbers. I got 165.5 plus or minus t star 1.796 times the standard error, which is s 18.22 divided by the square root of n, square root of 12. So I have 165.5 plus or minus. Now, need my calculator. .796 times 18.22 over the square root of 12. I get 9.446, so 9.45. Is that okay? All right, so 165.5 minus 945, this is 156.05. So on the low end, I have $156.05. And on the high end, I have 174.95. Okay. And so I would say I am 90% confident that the mean sales revenue, or mean weekly sales revenue of this vending machine is between 156.05 and 174.95. The end. Okay. Is that good with everyone? Makes sense? Okay, so let's say this is my confidence interval. This is my 90% confidence interval. All right, so let's just ask a very easy clicker question here. I think it's easy. All right, we'll say, does our confidence interval provide evidence against the claim that the average weekly revenue is $160? All right, here, well, let's change that. We'll say $168. Okay. Does our confidence interval provide evidence against the claim that the average weekly revenue is 168? All right, let's start this session. Okay, and then A will be yes, B is no. Okay, go ahead. Should be something's going on. Okay, let's take a look. All right, and that's correct. Okay. So basically, the answer is no. And what we say is 168 is inside the interval, right? So it is a plausible value for mu. Okay, and we'd say we do not have evidence against the claim that mu is equal to 168. Okay? But if we asked the question, does our CI provide evidence that mu is equal to 168, what would we say there? We would say no, okay? Our CI can never provide evidence that mu is some exact value. Right? I'm hoping this all sounds familiar regarding, because we covered very similar questions except it was about proportions, right? But now instead of talking about the proportion in the population, we're talking about the mean of our population. Okay, and then let me just change the, whoops, I did something here. This last question. Same as the top one, except it's going to say, does our confidence interval provide evidence against the claim that the average weekly sales revenue is, and we'll do some other number, 180, okay? And the answer here would be yes, okay? 180 is not inside our interval, or 180 is outside of the interval. So our confidence interval provides evidence that the mean is not 180. Okay. I went through this fairly quickly, but I'm hoping it's similar enough to what when we talked about proportions that we feel comfortable with this. So are we all good? Okay, I got a thumbs up there, and a head nod, and a yes. So that's feeling pretty good about myself there. Okay. I hope you've enjoyed the course. Give me a good review on your course evaluation. Yeah. So.
Only if you teach stats 20.
You know, I teach stats 102A, so the 102 series. So if you go, you know, we'll talk next week. All right, next topic: confidence intervals for the quantity. Mu1 minus mu2. Confidence interval for the quantity mu1 minus mu2 based on 2 samples. Okay. Here we are making a confidence interval for the difference between means, okay? We make a confidence interval for the difference, the quantity, the difference between means of population 1 and population 2. Okay? All right, and so, you know, just to kind of get us conceptually, let's just say, for example, this is an example. All right, let's say population 1, we'll say is men, okay? Just people, self-identified men, okay? And then over here, population 2, women, okay? And mu1 will be equal to the average height or the mean height of men in the population. And mu2 will be mean height of women in the population. I guess we're dealing with adult men and adult women. Okay. And we're going to create a confidence interval for mu1 minus mu2, okay? What we have is, you know, just in the US, mu1 is somewhere around, I don't know, 70 inches, okay? 5'9.5", 5'10", something around there. We'll just keep it simple. We'll say 5'10", okay? And then the mean height for women, somewhere around 5'4", 5'5". Let's just say 65 inches, okay? And so if we make a confidence interval for mu1 minus mu2 could be something like 5 plus or minus 2, which would be 3 to 7. Okay, now that might seem weird, but our confidence interval for mu1 minus mu2 might be 3 to 7 inches, okay? So our confidence interval for mu1 minus mu2 is, we'll just say, could be something like, could be 3 to 7, okay? We'll say 3 to 7 inches. Okay, so what exactly does this mean, right? What does this mean? This is not a confidence interval for the mean height of men, and it's not a confidence interval for the mean height of women. It's a confidence interval for the difference between the mean height of men and the mean height of women, okay? And so if we could imagine, if there were ever such a thing as, quote, the average man, or quote, the average woman, and no, this person doesn't exist, but if we could imagine such a thing, then this confidence interval represents kind of the interval, kind of a range of plausible values for the height difference between the, quote, average man and the, quote, average woman, okay? So it would be something like, our interpretation is, you know, we are, you know, blank % confident that the, quote, average man is somewhere between 3 and 7 inches taller than the, quote, average woman, okay? If there ever were such a thing, okay? Now, it's and that's all it is. It is not about individuals, because if we picked an individual man and an individual woman, that height difference could be all over the place, right? You might get a really tall man and a really short woman, and you might have a height difference of like a foot or something like that, okay? Or you might get a short man and a tall woman, and you might have a negative height difference, okay? Between, if you're calling sample 1 the men and sample 2 the women, okay? And in that case, you might get a negative height difference, all right? And so we're not talking individuals. We're talking about the average of population 1 versus the average of population 2, and we're making a confidence interval for the difference between those averages. Yes?
So the 5 is the difference between 65 and 70.
Yes, yes.
Where's the plus 2?
Plus or minus 2, I just made this up, okay? I skipped all of the math just to get us to the kind of the result and get us an idea of what we're talking about in the confidence interval. I want us to have an idea of what this confidence interval represents before we get into the math here, okay? Yeah, and I apologize for, you know, the gendered example, not necessarily just men and women as far as that goes, but it's a simple example, so I hope this quote kind of makes sense in terms of what we are going for with the confidence interval. We're not making a confidence interval for the average height of men and a separate confidence interval for the average height of women. We're making a confidence interval for the difference between the mean of population 1 and the mean of population 2. Okay, so let's work quickly. And so we're making a confidence interval for the quantity mu1 minus mu2. And so when we do that, we put x bar 1 minus x bar 2. This goes in our middle. This is the best guess that we have. Best guess for the quantity, mu1 minus mu2. And then we go plus or minus t star times the standard error. Same as before. Standard error just has this slightly crazy formula. It's not too bad. S1 squared over N1 plus S2 squared over N2. T star, you need your confidence level and your degrees of freedom. Degrees of freedom, df is still n minus 1, okay? But we have two n's. We have two n's, right? So what we do is we use the smaller of n1 and n2. All right, is that okay? I feel confident in you guys that if I gave you a set, you can identify all of these values, right? You just, identify, I'll say you need to identify x bar 1. For sample 1, you need to identify x bar 1, S1, and N1. And for sample 2, you need to figure out x bar 2, S2, and N2. And then you just plug everything in to the formula. And I'm confident that you guys can do that, all right? So can we skip writing out the example and filling in the numbers and doing all of the math? Okay, so I'm going to just jump to, and I'm going to say, all right, let's pretend that you guys did all of the math, and let's talk about the conclusions that we can make, because to me that's more important. The formulas are given on here. You're just going to look up confidence intervals, means, two samples, find the appropriate values, plug them in, get your results, right? Okay. So, can I flip to the next slide? All right, so let's say we made a confidence interval. So we'll say pretend. Pretend we make a confidence interval for the difference between the mean weight of golden retrievers and Labrador retrievers, okay? These are both dogs, by the way, okay? So these are like, I think the top two most popular dog breeds in the US right now. I had a black lab as growing up, but no more, right? That's okay. All right, so anyway, we make a confidence interval. We'll call golden retrievers. This will be population 1. And Labrador retrievers will be population 2. Okay? So let's say this will be, let's say our CI, we'll make our 95% confidence interval is 1.74 to 6.58 pounds. Okay? Our interpretation would be I am 95% confident that the mean weight of golden retrievers is somewhere between 1.74 pounds and 6.58 pounds more than the mean weight of Labrador retrievers. Okay. Someone comes along and asks, do we have evidence, or does the confidence interval provide evidence that the mean weight of golden retrievers is more than the mean weight of Labrador retrievers. Okay? Okay, and what is our answer here? Does our confidence interval provide evidence that golden retrievers, that the mean weight of golden retrievers is more than the mean weight of Labrador retrievers? The answer here is yes. Okay, we look at our entire interval is positive. Interval for mu1 minus mu2 is positive. Or another way is to say that 0, the value 0, is not inside the interval. Is not inside the interval. So we have evidence that there is a difference. Okay. Let me give you another example here. All right. So here we'll do we'll set this up. Pretend that we're looking at make a confidence interval for the mean weight of golden retrievers and Labrador retrievers. Let's say we take a different sample and we get a different confidence interval, and let's just talk about what happens then. Okay, I know some of you guys are writing, but I'm gonna flip the slide because we only have 2.5 minutes, 3 minutes left. Okay, so sorry. All right, so let's say our confidence interval this time goes from negative 2.1 to 3.1, okay? And we ask, so our interpretation here would be I am 95% confident that basically mu1, mean weight of golden retrievers, is somewhere between 2.1 pounds less and 3.1 pounds more than mu2. Now that might sound weird, and indeed it is. The question, the more relevant question is, do we have evidence that the mean weight of golden retrievers is different from the mean weight of Labrador retrievers? Okay, and the answer here is no. The value 0 is inside the interval, the confidence interval for mu1 minus mu2. That means it is plausible that the difference between mu1 and mu2 is 0, okay? Or that, yeah, I'll just write that. The difference is 0. Difference between mu1 minus mu2 is 0. Or in other words, it is plausible that there's no difference between these two means, okay? There is no difference between the means. So that means we do not have evidence that the mean weight of golden retrievers is different from the mean weight of Labrador retrievers. Okay, I hope that makes sense. We'll end here for today, and have a great weekend, and we'll see you guys on Monday.